Welcome to this Java Swing project, a glowing DNA helix built with math, perspective, and motion blur. Watch as code transforms into a smooth sci-fi animation. Now let's create a new Java class and call it DNA Helix Swing. Let's start by importing the libraries we'll need for our DNA Helix animation. From Auth we bring in the core graphics classes. This is what lets us draw shapes, colors, and handle 2D rendering. Next, from Event, we import event utilities, which we'll use to set up our animation timer and handle action smoothly at 60 frames per second. From Geom, we get access to geometric shapes like ellipses, lines, and gradients, perfect for drawing glowing particles and connecting lines between the DNA strands. We also import buffered image, which lets us create an off-screen buffer. This is how we'll add motion blur effects by layering frames instead of clearing everything instantly. Then we pull in utilities from java.util and java.util.list. These help us manage collections of particles and random values that give our animation a more organic look. Finally, from Swing, we import the Swing toolkit itself, along with JPanel for our canvas and timer to keep the animation running. With these imports in place, our project has all the building blocks needed to bring the DNA Helix to life. Next, we make our class extend JPanel. Now we set up the size of our canvas. We creating two constants, width 540 and height 820. Next, I create something called a buffered image named trail buffer. This image acts like an off-screen canvas. Instead of drawing directly on the window, we first render onto this buffer, then display it. Create a graphics 2D object called TrailG by calling createGraphics. Then, I declare a swing timer. This timer is the heartbeat of our animation. Now we set up the core parameters for our DNA helix. First, angle starts at 0, this will control the rotation of the helix as it spins in 3D space. Next, scroll also starts at 0, and it slowly increases to make the particles move upward, giving that endless twisting effect. The radius, set to 120, defines how wide each spiral strand is drawn. The pitch, set to 22, controls the vertical spacing of each turn, basically how stretched or compressed the helix looks. Then we have turns on screen, set to 9, which decides how many loops of the DNA are visible in the window at once. And finally, points per turn, set to 24, controls how many glowing particles we use for a single twist of the helix. Next, we set up two values that handle perspective. The first one is focal, set to 520. Then we set cameras to -420. Now we set some values that control the look of each glowing particle. Min size is set to 3.0, that's the smallest a particle can appear when it's far away. Max size is set to 9.0, that's the largest size when it's close to the camera. This way, particles scale smoothly with depth, making the 3D effect stronger. Then we have trail fade, set to 0.12. This number controls how quickly the motion blur fades out. Here create a random object called RNG, and seed it with the number 1337. Next, set up hue shift, starting at 0. Now we create a method called step, which updates our animation every frame. First, we increase angle by a tiny amount, here 0.7 degrees converted into radians. Next, we update scroll by 0.045. This moves the particles upward, creating that continuous twisting motion of the DNA strands. And finally, we increase hue shift by 0.0025. This gradually cycles the strand colors, giving our animation that glowing, futuristic vibe. Now let's look at the constructor for our DNA Helix Swing class. First, we set the preferred size of the panel using our width and height values, making sure the canvas matches the window dimensions. Then, we set the background color to black, so the glowing particles really pop against it. Next, we prepare our off-screen buffer called Trail G. We set its composite mode and immediately fill it with black, creating a clean slate for the very first frame of the animation. Then comes the most important part, the timer. We configure it to run 60 times per second. On every tick, it calls the step method to update the animation, and then repaint to redraw the frame. Finally, we call start method, which kicks off the animation loop, and from this moment, our DNA Helix starts moving smoothly on screen. Here we create a private static class called dot. Each dot represents a single glowing particle that makes up the DNA helix. It stores its 3D position with X, Y, and Z, and the projected screen position with SX and Psi. The size determines how big the particle is when we draw it, and alpha controls its transparency, making distant particles fade out. We also store a color for the glow effect, and strand, which tells us whether the particle belongs to the left or right side of the double helix. Finally, there's depth key, which is used when we sort particles from back to front, so the rendering looks correct in 3D perspective. In short, this dot class is the blueprint for every particle in the animation. Next we have the method strand color, which decides the color of each particle on the helix. If the particle belongs to the first strand, we start with a base hue of 0.56, that's a teal-like color. If it's the second strand, we start with 0.83, which is more purple. On top of that, we add hue shift, so the colors cycle smoothly over time. Then we set the saturation to a constant 0.85, giving us bright neon tones. The brightness speed depends on depth. Particles closer to the front look brighter, and ones farther away look dimmer. Finally, we return the color using HSB color mode. This small helper method is called clamp. It takes in a value and makes sure it always stays between a lower limit and an upper limit. If the value is smaller than the minimum, it returns the minimum. If it's larger than the maximum, it returns the maximum. Otherwise, it just returns the value itself. This helper method is called lerp, short for linear interpolation. It smoothly blends between two numbers, a and b, using a factor t that goes from 0 to 1. If t is 0, the result is just a. If t is 1, the result is b. And for values in between, it gives us a weighted mix. Now let's look at the drawings method. This is where we connect the two strands of the helix with horizontal lines, just like the base pairs in real DNA. Inside, we set up two lists of points, A and B. Each list will collect the screen positions of particles from one strand of the helix. Here we loop through the list of dots two at a time, since each pair represents particles from opposite strands. We grab the first dot as D1 and the second as D2. Then we check which strand the first dot belongs to. If D1 is from strand 0, we add its screen position into list A, and the partner dot into list B. Otherwise, we swap them, putting D2 in list A and D1 in list B. This way, the two lists always stay aligned, so later we can draw neat connections between the left and right strands. Before we start drawing the rungs, we save the current stroke style into a variable called old. This is like making a backup of the pen settings. Now we loop through both point lists, taking pairs of positions, one from strand A and one from strand B. For each pair, we create a gradient paint, starting from cyan on one side and fading into magenta on the other. This gradient gives the rungs a soft sci-fi glow instead of a flat color. Then we set the stroke to be a little thicker, with rounded ends, so the connecting lines look smooth and organic. Finally, we draw a line between the 2 points, completing one rung of the DNA ladder. Repeating this step across the loop ties the double helix strands together with evenly spaced, glowing connections. After we finish drawing the custom rungs, we call set stroke, old. This restores the original stroke settings that we saved earlier, so future drawing operations don't keep the thick, glowing line style. Next we have the method draw glow dot, which handles drawing a single glowing particle. It takes in the particle's screen position, its size, its transparency level, and the color we want it to glow with. Inside the glow dot method, we first calculate a radius r by multiplying the particle's size by about 2.2. This makes the glow area larger than the actual dot. Then we store the x and y position as cx and psi, which will be the center of our gradient. Finally, we create an array called dist with the values 0, 0.5, and 1. These numbers mark the positions of our gradient stops, from the bright center, to the mid-glow, and finally fading out at the edge. Next, we define 3 colors for our glowing gradient. The core color uses the same red, green, and blue values as the particle's base color, but with strong alpha transparency, making the center bright. The mid color is slightly dimmer, with a lower alpha, so it fades as we move outward. And finally, the edge is completely transparent black, which makes the glow smoothly fade into the background instead of ending sharply. Now we create a radial gradient paint, centered at the particle's position, using the radius and the 3 colors we defined earlier, core, mid, and edge. This gradient gives us that smooth glow effect. Before drawing, we save the current composite mode, then set it to SRC over, which allows transparent blending. We apply the gradient as the paint, and finally fill an ellipse that's centered on the particle, with a diameter twice the radius. This paints the soft glowing halo around the dot. After drawing the soft halo, we add a bright core at the center of the particle. We reset the composite mode to SRC over, then pick a pure white color with some transparency, scaled by the particle's alpha value. This ensures the core looks bright but still blends naturally. Next, we calculate core as about 90% of the particle's size. With that, we draw a small white ellipse right at the center. Finally, we restore the old composite setting so future drawing isn't affected. This combination of halo plus core makes the particle shine like a glowing light source. Next we have the draw vignette method. A vignette is a subtle dark fade around the edges of the screen that helps keep the viewer's eyes focused on the center. Inside the vignette method, we first define an array called dist, with values 0 and 1. This marks the start and end points of our gradient. Then we create a matching array of colors. At 0, the center, it's fully transparent black. At 1, the edges, it's a soft black with a little opacity. Finally, we build a radial gradient paint, centered on the middle of the screen, with a radius that's about 60% of the panel's size. This creates a smooth fade from clear in the middle to darker at the edges. Before applying the vignette, we first save the current composite settings into a variable called old. Then we switch the composite to SRC over, which allows our gradient to blend smoothly on top of the existing frame. We set the paint to our radial gradient, and then fill a rectangle that covers the entire screen. This lays down the soft edge shading. Finally, we restore the original composite so the rest of our drawing isn't affected. That's how the vignette gently darkens the edges while keeping the DNA helix glowing in the center. Next comes the Draw Subtitle method. This is where we add a little text overlay at the bottom of the animation. Inside the subtitle method, we start by creating a string called title, here set to DNA Helix. Next, we set the font to bold with a size of 16 points, so the text is clear but not too large. We then use font metrics to measure the exact width of the text. That allows us to calculate the X position so the title is perfectly centered on the screen. Finally, we set the Y position near the bottom, just 28 pixels above the edge, so the text looks neatly placed without overlapping the frame. Here we first set the color to a semi-transparent black, with an alpha of about 110. Then we draw the title string slightly offset, 1 pixel to the right and 1 pixel down. Next, we set the color to a bright cyan with high transparency, giving it a glowing neon look. Then we draw the title again at the original position. Now let's move into the render frame method. This is the heart of our drawing process. It's called every frame to update the visuals. To start the render frame, we enable high-quality rendering. The first line turns on anti-aliasing, which smooths out jagged edges on circles and lines. The second line sets the rendering mode to quality, telling Java to prioritize smooth visuals over raw speed. Next, we calculate the center point of the screen by dividing the width and height by 2. This gives us Cx and Psi, which we'll use as the origin for projecting our 3D coordinates onto the panel. Then, we create a new list called dots. This list will hold every particle of the DNA helix for the current frame. Here we set up 2 key numbers for building the helix. Total turns is equal to turns on screen, which controls how many loops of the DNA are visible at once. Then we calculate total points by multiplying the turns by points per turn. Now we start a loop that runs through every particle we need to draw. It begins at -half of the total points and goes up to +half. By doing this, we generate particles both above and below the center. Inside the loop, we calculate a parameter t, which represents the particle's angle around the helix. It's based on the loop index plus the scrolling offset, multiplied by 2π over the number of points per turn. Next, we compute z-base by multiplying the index with the pitch. Now we start another loop for the 2 strands of the DNA. Since there are always 2, we run this loop twice, once for strand 0 and once for strand 1. For each strand, we first decide the phase. If it's strand 0, the phase is 0. If it's strand 1, the phase is pi, a half-turn offset so the strands sit opposite each other. Next, we calculate the 3D coordinates. The x position is the radius times the cosine of the angle plus phase. The y position is the radius times the sine of that same value. And the z position comes from z base. We calculate cosa and sine from the current rotation angle. Then we apply a simple rotation formula. Rx is the rotated x-coordinate, mixing the original x and z values. Rz is the rotated z-coordinate, also combining x and z but with opposite signs. And y just stays as y, since we're not tilting up or down. This transformation makes the helix slowly twist in 3D space as the animation runs. We shift the z position by adding cameras, which moves the whole scene away from the viewer. Then we calculate a scale factor s, using the focal length divided by focal minus c cam. Finally, we get the screen coordinates. Sx is the center plus the rotated x times the scale, and psi is the center plus the rotated y times the scale. Now we adjust how the particle looks based on its depth. First, we calculate depth norm, a normalized value between 0 and 1. It tells us how far the particle is from the front to the back of the helix. Next, we use lerp to smoothly scale the particle's size between a minimum and maximum. The closer the particle is to the camera, the larger it appears. Finally, we set alpha, which controls transparency. Particles in front are more visible, while those farther back fade into the background. This depth effect makes the helix feel truly three-dimensional. Once we've calculated all the properties for a particle, we wrap them into a new dot object. We store the rotated 3D coordinates x, y, z, and the projected screen coordinates sx, psi. We also save its size in alpha, so we know how big and how transparent to draw it. The strand tells us whether it belongs to the left or right side of the DNA helix. The depth key holds the scale factor, which we'll later use to sort dots from back to front. And finally, we give it a color by calling strand color, passing in the strand index and depth. With everything ready, we add this dot into the list, so it can be rendered with all the others. Once all the particles are generated, we sort the list of dots by their depth key. After sorting, we call draw rungs, which connects matching dots from each strand with glowing lines. Next, we loop through every dot in the list. For each one, we call draw glow dot, passing in its screen position, size, transparency, and color. This method paints the glowing particle with a soft halo and a bright core. We call Draw Vignette, which darkens the edges of the screen so the viewer's focus stays on the center. Then we call Draw Subtitle, which writes the title text at the bottom, giving the animation a clean, professional look. Next we add a helper method called Add Hotkeys. This wires up keyboard shortcuts for our panel, so the demo is easy to control while it's running. We first grab the panel's input map, telling Swing we want to listen for keys even when the panel just has focus. Then we fetch the action map, which will hold the actual commands to run when those keys are pressed. Here we bind the escape key to a custom action called Quit. In the input map, we say that when escape is pressed, it should trigger the action named Quit. Then, in the action map, we define what that action does. Inside action performed, we simply call system exit method. That means pressing escape will instantly close the program, giving us a quick way to exit the animation. Next, we bind the spacebar to a custom action called Pause. In the input map, pressing space triggers the action, and in the action map we define how it works. We keep a Boolean flag called paused, which flips every time the key is pressed. When paused is true, we stop the animation timer, freezing the helix in place. When paused is false, we start the timer again, letting the animation continue. This gives us a simple, keyboard-controlled way to pause and resume the DNA Helix on demand. Now we override the paint component method. The very first line calls super paint component, which clears the panel before we start drawing. Inside paint component, we first work on the trail buffer to create our motion blur effect. We set the composite mode to SRC over, so the new drawing blends with what's already there. Then we pick a nearly transparent black color, where the transparency is controlled by trail fade. Finally, we fill the entire buffer with this color. Instead of wiping everything clean, this slowly fades the old frame, leaving behind smooth glowing trails as the helix moves. After fading the previous frame, we call render frame on the trail graphics. Finally, we take the completed trail buffer and draw it onto the panel. We create a fresh graphics 2D object from the original G, so we don't mess with the default settings. Then we enable bilinear interpolation, which smooths the image when it's scaled or blended. After that, we draw the entire trail buffer at the top left corner of the panel. And once we're done, we call dispose to release the graphics context. This finishes the paint cycle, showing the updated DNA Helix on screen with smooth trails and motion blur. Now we come to the main method, which starts the whole program. We use swing utilities invoke later to make sure the user interface runs safely on the event dispatch thread. Inside, we create a new JFrame titled DNA Helix, Java Swing, and set it to close properly when the window is exited. Then we create an instance of our DNA Helix swing panel, which contains all the animation logic and drawing code we built earlier. Before showing the window, we call add hotkeys, so our panel responds to escape and space for quitting or pausing. Then we set the panel as the content of the frame, and call pack, which sizes the window to match the panel's preferred dimensions. Next, we center the frame on the screen with set location relative to null. Finally, we make it visible, and our DNA Helix animation is ready to run. Thanks for watching this DNA Helix animation in Java Swing. I hope you enjoyed learning how math and code come together to create sci-fi visuals. Don't forget to like the video, share it with friends, and subscribe to the channel for more creative coding projects. See you in the next one.